So for the concept of growth and decay, we know that bacteria increases their quantity by dividing after a certain time. On the other hand, a radioactive substance has a half-life which is determined by the time it takes the radioactivity to fall into half. This reality gave rise to the concept of growth and decay. In solving a growth problem, we let x be the amount at any time t, x naught be the initial amount when t is equals to 0, and the derivative of x with respect to t be the rate. So the growth rate is directly proportional with the amount present at any time. So in order for us to solve the amount at any time, we use variable separable and integrate both sides. Solving this differential equation, we'll come up with this equation ln x evaluated from x naught up to x and k t evaluated from 0 up to t. So it follows that ln x over x naught is equals to kt. Simplifying this equation will yield to x over x sub o is equals to e raised to kt. So the amount at any time t will be equal to x naught times e raised to kt. So for problem number 1, let us first tabulate the given data. Initially, we have 50 strands of bacteria at t is equals to 0. So after 7.5 hours, the number of bacteria double, and we are asked to determine the number of strands after 1.5 days, which is equivalent to 36 hours. So let us first solve the value of k using this formula that we derived a while ago. So ln x would be 100, this one is the x, and this one is xo over 50 is equals to k times 7.5. So the value of k will be 0.0924 per hour. So to solve for the expression for the number of bacteria in the milk, and then x is equals to xo. Substitute the value of k. T. So this is now the expression for the number of bacteria in the milk. So to solve for the number of bacteria present in the milk after 36 hours, so we use this formula. We substitute the value of x naught, which is 50, and also RT, which is 36 hours. So solving for this, we will get a value of 1,393 bacteria. So for problem number 2, which is the disintegration of radium, we first tabulate the data. Initially, we have 100 milligrams at T is equals to 0, and then 96 milligrams after 1 century. And we are asked to determine the amount present at 2.56 century and also the half-life of the radium. So, in solving for this, we first solve for the value of K. So, as you can notice, it is just the reverse of the growth. The numerator will be the x naught and the denominator will be the x. So, the value of K is 0.0408 per century. So, we will now solve for the value of x at 2.56 centuries, and we will use this formula. X is equals to x naught e raised to negative k times t. So substitute the value of x naught, which is 100, and then e raised to negative 0.0408 times 2.56, which is the time. So solving for this, we will get x is equals to 90.08 milligrams. And to solve for its half-life, we use the equation T sub 1/2 is equals to ln2 divided by the value of K. So we will have ln2 over 0.0408. So the value of our half-life is equals to 16.99 centuries. 16.99 centuries.
Newton's law of cooling is used to model the temperature change of an object of some temperature placed in an environment of a different temperature, and also to determine the victim's time of death. For the Newton's law of cooling, the rate of the body's temperature changes directly proportional to the difference between the temperature of the body and the temperature of the surrounding. By integrating this side from T naught to T, we come up with ln of T minus Tm all over T naught minus Tm. And by integrating this side from 0 to T, we come up with Kt. And for simplifying the equation, ln of T minus Tm all over T naught minus Tm is equal to Kt. for the first problem of Newton's law of cooling, we tabulate first the data, so temperature and for the time. Here, we should find the temperature after 8 minutes. The temperature of the environment is equal to 65 degrees Fahrenheit. We use the formula ln of T minus Tm all over T naught minus Tm is equal to Kt, where our T will be the 40 degrees Fahrenheit and Tm is 65 degrees Fahrenheit, and our T naught will be 24 degrees Fahrenheit. And for our time, 5 minutes. So we will get K is equal to negative 0.09894 per minute. We will use the formula T is equals to Tm plus T naught minus Tm times e raised to Kt. T is equals to 65 degrees Fahrenheit plus 24 degrees Fahrenheit minus 65 degrees Fahrenheit times E. Substitute K, E raised to 0.0984 times 8. So our T will equal to 46.42 degrees Fahrenheit. Problem number 2. Tabulate first the data. T, so for the time, 100 degrees Celsius, 0, 60 degrees Celsius for 10 minutes, 20 degrees Celsius, and you should find the time for the F minute. Our Tm is equal to 5 degrees Celsius. We use the formula ln of T minus Tm all over T naught minus Tm is equals to Kt. For our T is equal to 60 and our Tm is equals to 5. our T naught is equal to 100, and Tm is equals to 5. Is equal to K times 10 for the difference of 10 minus 0. Our K is equal to negative 0.05465 per minute. And for computing for the TF minute, use the formula ln of T minus Tm all over T naught minus Tm is equal to KT. For our T is equal to 20, for our Tm is equals to 5 all over, for our T naught 100, for our Tm 5 is equal to, for a value of K, negative 0.05465 multiply by T. For simplifying it, T is equal to 33.78 minutes.